Good morning. How's it going?
Hello, everybody. Welcome to Devternity Edition 2020 second. It's the biggest one so far, and I'm glad to see so many people joining this event. Hopefully, everything's gonna be good for you, and you are gonna have a productive day. So, yeah, our first speaker today is Mr. Kevlin. So, yeah, why don't we just get started? So, please welcome Kevlin, and yeah, the mic is yours.
Excellent. Thank you very much. Okay, so good morning and good afternoon and good evening, depending on your time zone and when and where you are watching this. Let me share my screen because we are going to talk about code. Question mark. What do we mean by it? We use this word all over the place, and I want to take a look at spend the next 50 minutes looking through some of the things. I mean, in fact, I actually had to cut this talk down because, as you can imagine, this is actually quite a large topic. And there's a number of topics I've touched on in the past, some of them in Devternity, and so I'm going to continue certain themes, but also a few others that I've picked up. And then there's a whole load I had to delete because I suddenly realized, you know, this is 50 minutes, not 50 hours. So if you have any questions, I'm not going to have any time for questions at the end of the talk within the 50 minutes. So what I suggest is if you have questions concerning anything that I'm saying during the talk, feel free to pop them up in the Slack channel. It's Devternity Track 1. I've got that open on a screen. So I may not respond synchronously, and I'll make a judgment as to whether or not I think, oh, yes, I can respond to that in the context of the talk or not, or I will answer questions there on Slack afterwards. So, yeah, so here we are once again, not in the real world, back online. So this is what I look like in the real world. And then there are all my social details. If you want to get in touch with me, and connect with me or ask me anything else following this talk. But let's talk about code. So this is the question. What do we mean by it? This is a word that comes down to us from Latin. We can use it as a verb, but I'm going to focus on it just for the moment. I'm going to give you a series of definitions of the ways that it is used within software development, but outside. So let's start with something simple. A set of conventions or principles governing behavior or activity in a particular domain. That's like a code of conduct. A code of conduct, a kind of a code of practice. We use the term code here, and we can reframe, and we can often make things explicit. A very good example of this. So in other words, we can take a social idea, and we often think of social ideas as being fairly abstract and loose. We can take a social idea and make it more concrete, and we can respond to things, and we can change our own awareness and perception of them. A very good example of this in terms of a code is from April Wenzel. She talks about compassionate coding, and very much a way of trying to be, I guess, a little more human about how we relate to our colleagues as well as our profession. And so this is offered up as effectively as a code. Rather than ego, we should suggest humility. You know, you don't know everything. You might be wrong, and that's okay. Rather than elitism, we do accidentally do a lot of gatekeeping. Inclusion. You know, it's just like, honestly, I enjoy coding. Why would I want somebody else to not enjoy it? You know, just you want everybody along for the ride. This is a knowledge-based profession. So knowledge is something that I think wants to be shared. Rather than competitive approaches, cooperation is far more useful. Competitive approaches, particularly within companies, is surprisingly destructive. It leads to excessive distrust. I've met people who sort of said, oh, I'm not going to comment my code because other people might be able to take advantage of it, and then I won't have a special place in this company. It's just like, well, hang on, that's not really a healthy way to look at it. And perhaps there's a reason that you ended up thinking in those ways, but we can always revise it. Learning. And often we put too much value in what we call the fixed mindset. In other words, you know stuff and you're always considered to be good. Actually, it's okay not to know stuff. In fact, more importantly, I said that software development is knowledge-based. you are always operating with incomplete knowledge. That may be one of the most important things. You are operating with incomplete knowledge. You will never know everything that you need to know to write the code that you are writing today. The time at which you will know is sometime in the future, but you still have to make progress today. Guess what? That's a human superpower. We are able to make progress without knowing everything. But the first thing you have to do is acknowledge that. This also influences how we develop our code, how we develop our systems, because we have the idea that we will learn more as we progress. Therefore, we need to create our code, our source code. We need to create our code in a way that can be changed so that as we learn, so does the code. The very definition of a legacy system is a system that has not been able to keep up with our learning. We know more, but are unable to put it in the system. The system resists it. So learning is fundamental to what we do. The whole rockstar thing, I've really never been a fan of that terminology. Being a mentor, learning is there to pass on. So that's kind of one approach, thinking about code in terms of a set of guidelines, community-wise. Historically, we also use it as to represent a system of figures, words, or symbols used to represent others. We have one thing to stand in place for another, to sometimes stand in place for an idea. So at the moment, the Artemis 1 probe is currently returning to Earth, having done a retrograde orbit of the moon, quite eccentric retrograde orbit of the moon, laying the path for return of human flight to the moon. But let's go back to 1969 and the first lunar landing. Here's some codes. They had the first flight system on that, the Apollo guidance system. A number of people at MIT developed that. And there were basically all those lovely error messages that you get now, and all the expressive programming languages. There were some really good decisions taken for the AGCS, but obviously error messages in a tiny LED display, there were no messages. You had to use a code. And therefore you couldn't easily change this code. Classic example of hard-coded numbers. And so therefore you had to know the numbers. And so there was a lookup. I actually have a copy of a reprinted copy of this. But this is taken from the original kind of handbook of development. 1201 and 1202 errors plagued the Apollo 11 lunar lander as it descended towards the moon. And these were actually to do with overflow errors, to do with the fact that the executive of the runtime was overloaded with work. And that was actually a kind of a side effect of leaving the radar on, which is flooding the system with too much data as it was descending. So basically the computer it just didn't have enough resources. And what it was doing was actually dropping the low priority tasks. A lot of this comes down to a woman called Margaret Hamilton, who basically created the concept of fault tolerance in flight systems. So here we have a code, but not everybody was aware of it. So if you listen to the transcripts or read the transcripts of the landing, and there's a great podcast, 13 Minutes to the Moon, that really goes through everything. They talk about 1201 and 1202, what's that? And they clarify that. We have other encodings as well. Biquinary coded decimal, a system of counting in fives, okay, but decimal. So in other words, just like our hands, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, depending on how you want to do it. Now, that means that we break our tens into two groups of fives, and we have a lower and an upper amount. This is used on traditional abacuses, or that you still actually find in some parts of the world. It was also used on a number of early computers from IBM and Sperry, and in fact the Colossus, so 1940s and 1950s, before people figured out, you know what, binary is a lot easier. But the most common biquinary coded decimal system that people are likely to come across on a day-to-day basis is Roman numerals. So Roman numerals, they are in groups of 5. If you think about it, you have 1, 2, 3, 4, 5, 5 has one particular symbol, and then 6, 7, 8, 9, 10. 10 has a different one, and we see this patterned throughout the number system. So we have that, but we can also do other encodings. So I'm going to take you back to 1932. We've done 1969. Let's go back to 1932. Alonzo Church invented lambda calculus, but it didn't really come to its own until 1936, when he really applied it for a successful proof. It turns out this proof was not successful. An unsolvable problem of elementary number theory, which actually relates to, from our point of view, things like the halting problem, and whether or not things can be computed. So this is quite interesting, but he created a separate calculus for that. And in doing so, he created a code. That is what, whenever you choose any notation, that's what you're doing. Whether it's DSLs, mathematical formula, or you're inventing new branches of physics, or secret languages with your siblings. We select a particular list of symbols consisting of curly brackets, parentheses, lambda, and square brackets, and an innumerably infinite set of symbols A, B, C, etc. to be called variables. And we define the word formula to mean any finite sequence of symbols out of this list. So lambdas, a lot of people are familiar with lambdas in their languages, or at least things called lambdas. It turns out that many of the things that are called lambdas are not actually lambdas. They don't follow the true rules of lambdas. So Java lambdas are not yet lambdas. C# lambdas are almost lambdas. But if you're working in a number of other languages, whether it's Python or Ruby or C++, these languages actually have lambdas that are pretty much closer to the original definition. Here on the screen, we actually see a very simple example. We see a lambda that takes one parameter f, and then there's nested within that, there is a formula that is a lambda that takes a parameter x, and then we actually have the result, which is x. This is kind of faking up taking two parameters. It turns out that lambdas only take one parameter in their original definition. And you can see that x is just returned. F is never applied, it's never used. And to be precise, it's applied 0 times. Now, this is the kind of interesting thing, because what Alonzo Church did is he created an encoding called Church numerals. He reinvented the numbers to make proofs about them. So 1 is this, we apply F once. 2 is applying F twice, and so on. The idea here is that numbers correspond not to things, but to doingness or application. And so doing something no times is 0. Doing something once is once. Doing something twice to itself. And so these are the Church numerals. Now, in some functional programming languages, you can kind of fake them up. And even in Smalltalk, it's based on Church encodings, some of the ideas in there for particularly Boolean numbers and the way that for loops work. So we can kind of describe it like this. Church said, actually, you know what? Let's do a shorthand notation, even though it's one parameter, we'll allow 2, and that's a shorthand for this. And they also introduced other shorthands to make it a little bit easier to write these things. But another encoding system we can use comes from the 19th century mathematician Giuseppe Peano, where we can actually describe all numbers from a starting point and a successor function. So in other words, 1 is the successor of 0, 2 is the successor of 0, 3 is that, and we can define the successor function like this. So we got an encoding. So we can do it like that, or even easier. 1 is the successor of 0, 2 is the successor of 1, and so on. So lambda calculus actually has some very different origins to the way that we use it in code these days, but it is an encoding system. And you can even encode numbers, Booleans, linked lists, which gives ultimately our ideas of head and tail and the way we think about those when we think of linked lists. Now, there's a lovely quote from Andrew Koenig in the 1990s. He said, people who brook no compromise in programming languages should program in lambda calculus or machine language. The idea, they're both pure, but different kinds of pure. One is pure at the machine level, one is pure at the mathematical level. The godfather of computing, John von Neumann, also, he was a polymath, an impressive individual in terms of his intellectual achievements and what he contributed. But he was critical of anybody trying to create high-level languages. Why would you want more than machine language? He just didn't understand, And notice he's saying, why would you want more than machine language? Assembler is too high level for him. So we have the idea of code as a set of symbols. But actually, let's elaborate that definition. A system of words or words, figures, or symbols used to represent others, especially for the purposes of secrecy. We talk about this in terms of coding and code breakers. In fact, many software developers end up being code breakers because the problem is we often write our code in code. And when we talk about legacy code or other people's code, that's another way of talking about it. When we talk about legacy code, people often say, oh, well, I don't understand it. It's like it's written in code. So we have two meanings of code playing with each other here. So back to Roman numerals. Roman numerals, you may notice, are used in a few things. I think in America, they're used to number the Super Bowl. In a lot of films, if you look at the copyright messages, a lot of them will actually be in Roman numerals. In fact, in the UK, they used to use Roman numerals so that you couldn't easily tell when a program had been made, and therefore you could repeat it without people going like, wait a minute, this is an old program. Most people can't read these comfortably. This is 1977, which was the year of release of Star Wars. We can also do other things with our code. I was talking about legacy code and obscurity. This is an entry from in fact, it's the winning entry from the 1989 International Obfuscated C Coding Contest in the best layout category. So this contest is write obfuscated C, write some C that is intentionally obscure. Okay, it should be playful, it can be exploratory. There's a lot of possibilities here. So what we see here is some code that has been formatted. It's legal C code. It's been formatted as pi. The great humor here is, how does it do it? And you will notice all the way through, it uses the opening digits of pi in various forms. Variables are named like this, hence the leading underscore. So this recurrent theme, it screams pi at you. And do you know what it does? It calculates E, the Euler number. It's absolutely brilliant. Then we have other things. This is what is known as an illegal prime. So this is a prime number, and in 2001, so it's 1,000 digits in length. And the thing about this, it's called an illegal prime. Why is it illegal? Because if you write this one out in hexadecimal and you use those as the bytes and you put that into a file, then that is the gzipped, that is basically the compressed version of C source code that can be used to break the DRM on DVDs. And given that that was illegal, this is known as an illegal prime. So basically you can take this number, turn it to hex, drop it out as bytes, run gzip or gunzip on it, and you will have yourself a little piece of C code. Now, obviously for us, normally the most comfortable way of thinking about code is always about a computer, a set of instructions for a computer. And that can be, when we use the term instructions, that suggests something relatively low level, although sometimes we think of it as high level. Instructions is very imperative, quite different perhaps to, say, Lambda thinking and declarative approaches. So this is some example code. This is from the Apollo guidance system. It's part of the engine control. And this is written, this is the resulting assembler. The original was, there's a lot of really interesting things about the hardware. It was 14-bit, okay, forget 16-bit, 8-bit, 32-bit, all the rest of it. It's 14-bit. Clock speed, yeah, kind of slow by modern standards, 43 kilohertz. And the memory was 36K, which is actually quite a lot for the time. That's a lot of memory there. And the code was, the language was called Mac. This is the resulting assembler from it. But the high level code, Mac, MIT algebraic compiler, it was hand compiled. If you wanted things to be reliable, you hand compile. That literally means you've got rooms full of people sitting there with books of how to translate the code into assembler. And to make sure that it worked, you had different independent teams, and then they check their results. But they also transferred the comments through, and the comments I think are particularly interesting. Here we see a state model being described. Here is the philosophy of Guildenstern. On every appearance or disappearance of the manual throttle, discrete to select P67 or P66 respectively. On every appearance of the attitude hold, discrete to select P66. These are program numbers. Unless the current program is P67, in which case there is no change. So it's a very simple state model that is describing what the code is doing. Now we can see that comments have a certain role to play in assembler. Assembler lacks structures such as indentation and nested branching. I noticed that some people these days have decided they don't want to do nesting and they're going back to assembler. I see this practice increasing in high-level languages, which fills me with sadness and despair. I think we need to learn. I think we need to learn how to program again. Many people really don't know how to use else statements, I've noticed as well. Anyway, that's a separate rant. Let's talk about this one. I love this. My favorite comment in the source code. Temporary. I hope. Temporary. I hope. Here we are in the 21st century, looking at somebody commenting on a temporary workaround, which is clearly very permanent. You know, this is over half a century later. So there's this interesting thing about comments and code. In fact, you can actually hear it in the way that I'm saying it. Here's, you still find this on, this is on the Oracle website for Java. It's a hello, this is hello world. This is ridiculous. Look at the copyright symbol. It uses all three forms of Java comment. If you like, you've got the free format version, you've got the Javadoc version, and then you've got the line-based version. You've got all three forms of comment. This is a big copyright message because obviously this is something that you would care a great deal about, and you know, you really need to make sure that you've got to retain the copyright. So I've retained the copyright message here because we need to know that the people at Oracle don't do code reviews. That's what we need to know. That's what this teaches us. Because when we look at it, I mean, it's not just the fact, I mean, if I were in a code review, I'd say, hello world app. Isn't app a little bit generous for this? But actually the simplest thing here is, why are you telling me that you're displaying the string? That's very pointless. Likewise, this is fairly pointless, but the most problematic, there's a missing comma. There should be, it's hello, comma, world is the correct way to write this using standard English. So clearly they don't have this idea of code review and the simple fixes, but by goodness, look at this. So when we talk about code, most people, so we use code in this very fluid way. I've already given you a number of definitions, but for most people, they would say code is the bit that actually kind of runs. Well, that's kind of interesting because there's only one line here that actually runs. The rest is declarative noise. So people would call this code. They wouldn't necessarily call this code, but we would still say this is source code. We would normally just describe this as comment. And we distinguish between the two categories. And honestly, most comments need to really be just deleted, and nonsense like this. If you're ever going to put big copyright messages, if you do feel the need to do that, or your company feels the need to do that, don't put them at the beginning. That's a ridiculous place to put them. Put them at the end, because people don't want to see that when they open up a source file. That's why you, in most IDEs, you can fold away comments. Why do I want to see this? Think about how you watch a film. All of the credits are at the back. Okay, all the copyright messages are at the back, at the end of the film. Okay, feel free to put a kind of like mid-credit scene in if you like, but people open the source code file to see the source code. They do not open it to see that. Don't bore your reader, make them interested. So here's a picture of me from 20 years ago. I've been talking about comments since the 1990s. This is from a column that I used to write for Application Development Advisor magazine. I prefer code to comments. And that's an notice here. I've also got this bias. I am talking about code, the stuff that runs, as separate from comments, even though clearly comments are part of the programming language, are part of the source file. comments are an odd form of code. They are code that is not code. That highlights that kind of paradox here. So let's talk more generally. A computer program or a portion of a computer program. And we've seen a couple of comments in the comments in the threads. And a good one from Nico. Only good comment is a temporary to-do marker, ideally removed right after the next refactoring cycle. In fact, I sometimes recommend to people that they make the idea of no to-dos in the code part of their check-in. Okay, in other words, your basic criteria. Don't check in code that doesn't compile. Do not check in code that has to-dos. Okay, a simple definition of done. Okay, so otherwise it accumulates over time and you just create noise. Okay, you gotta keep things clean. So in general, let's talk about this idea. So, but notice I'm not saying you shouldn't have comments. Be very careful. Sometimes people get a little carried away and say no comments at all. Comments derive their value based on scarcity, like many things. So I live in Bristol in the UK. It's one of the wettest parts of England. Where I live, water is quite common. It's pretty wet here. Obviously not today. It's bright and sunny and cold, but most of the time there's a lot of rain. So water is not valuable. Whereas if you move to a desert climate or a more southern climate from here, you will end up with less rainfall. Therefore, water is more valuable because it is scarce. So in other words, the value of a comment is defined by the scarcity of comments. If you comment everything, comments are not valuable. And they will also mostly be wrong, which also decreases their value. You end up with deflation. I want comments to be so valuable that there's no other way of saying something. In other words, I tried to express myself in code, but there was no other way to do it. In other words, everything I could do to put it in code was in code, including in tests. Tests are a form of your code. Check-in comments are valuable comments. They are meta data about your code because they also describe the history of your code. So there's a lot here because we saw a mention of Git and so on in this context. Anyway, let's talk about code. Actually, I'm going to pick up a comment from Christians here about code comments. I've not found ways to express the business requirements or reasoning behind certain architecture approach in code itself. Now, some business requirements, so this is why I often mention tests. Tests are, think of your tests as documentation. When you think like that, you will write your tests differently. That is where you comment many of these things. If there are business constraints, that is the name of your test. So first of all, we need to embrace the idea that tests are code. Sometimes people have a bit of a blind spot about this one and don't treat them as first-class citizens. And then the idea of actually this works really well to express my requirements formally in a way that is maintainable and visible. It's to do with the visibility. Now, for some architectural decisions, the code is not always the best place to put the comments in, and I would recommend you have a look at architecture decision records, ADRs. Again, that goes back to the version control system way of thinking about things, and that's a really good place to put your architecture decisions. I'm actually going to mention those tomorrow in my Architecture with Agility talk. Let's talk about computer programs, because we have been for the last 25 minutes, but let's go in a little more detail here. I'm often known on social media by the fact that a lot of people tweet error messages that they see in public places to me. These have become known after me because I normally retweet them at Kevlin Henney's. For a lot of examples of code that are supposed to be hidden, we lose the encapsulation. Our customers see the code. In fact, I love this one. This was Ryan Sloboyan sent this one to me from Canada, where it had made, we can actually see that not only do they use English and French in Canada, they also use PHP. We actually see the code visibly there. So mistakes, this is the one thing we have learned. And in fact, in the 1950s, people underestimated hugely the degree to which we would have bugs. It turns out that bugs are normal. Many papers are flawed with bugs, and so a big concern of ours is writing programs that work, writing correct programs. Bugs are basically a form of waste, and they hold back software development. So let's go back to 1983. Yeah, we're doing a lot of time travel today. John Bentley used to have a column in Communications of the ACM, and these were collected, it's called Programming Pearls, and this was collected into some books. And he had a special, he wrote one of his columns on how to write correct programs, and he was a big fan of formal methods at this point in his career. And so here we see, here we're going to see actually there's another form of code that I'm showing you. This is pseudocode because this is not a programming language. It is kind of C meets Pascal. It also has comments in it. That's the things in the curly brackets. And those things in the curly brackets are effectively assertions. And based on these assertions, these invariants that must be true at various points, he has got a proven approach. So this is a binary search algorithm. Actually, when he presented it, it was a novel binary search algorithm. And it will, so binary search is, it will show you the position where you're supposed to be, or it'll show you the position of where something is in an ordered array. Okay, so a sorted array, it will find the occurrence of a value or where that value should be. This is different to some binary search algorithms, which basically just say either it's there or it's not. This is slightly better. It says it's here, or if it's either here or if it were here, it would be in this place, which is great for insertion. And so he then goes through in the paper and he proves that this works. And indeed, there's you actually notice, let me just highlight, he put it as case here. This is a three-way condition, so a high-level kind of case statement. It's an if-else, if-else, if by any other name. And he, so the idea here is that we've got a three-way division. And we can see that three-way division reflected here. Now, this code was written by Josh Block, who was a student of John Bentley's and was also the developer of the Java Collections API. So Josh used to work for Sun. And so we've got all of this. Now, this code was in the Java distribution for a very long time, in fact, until, in fact, 2006. So, by the way, although it's there's some other conversations going on Slack, but there's some really good stuff that people are saying, very useful and constructive stuff on some of the things, building on comments, ADRs, wikis, things like that. So if you want to, there's a good load of stuff here that you want to go back to and look at. So anyway, remember this algorithm was proven correct. There's only one problem with it. In 2006, it was discovered to have a bug. That bug is around this, because it turns out that code is not mathematics. It's not the mathematics you learned at school. When you add two numbers, let's just take two large positive numbers. When you add two large positive numbers, what you're taught at school is you get a much bigger positive number. We are trying to find the average or the midpoint between two values, low and high. Okay, imagine we're searching through an array, and this is an index, the low index and the high index of where you're trying to search between. If these two numbers are really large, they don't add together to create a large one that you then divide by 2. They add together to create a negative one, because integers wrap around, because integers are not integers. Integers in mathematics are infinite. They have a cardinality of Aleph null. They are countably infinite, whereas in most programming languages, integers are bit size bounded, and even in those which have arbitrary sizing, you're still bounded by memory. But here we are bounded by Java's ints, which are 32-bit, and that means when you get two very large numbers and added together, you will end up with a very large negative number and divide that by 2, which is a negative index, which is not allowed. Now, this would not have been detected in the 1980s because the kinds of numbers we're talking about here, you simply didn't have the memory for. You'd never have an array that large. So there's a huge irony in the fact that this article is called Writing Correct Programs. In fact, we even have, as well as the word irony, we even have, there's a wonderful law, Muffrey's law, that arose in the context of writing, but we can see that here. If you write anything correcting or criticizing the quality of someone else's editing, proofing, spelling, grammar, there will be some kind of editorial error in what you've written. In other words, if you are writing something on how to proof correct programs, there's a chance that there will be something wrong with it, will be incorrect in some way. From our point of view here, Muffrey's law is, as it were, a specific application of Murphy's law. In other words, it's a misspelling. So how do we fix this? We can fix it by doing this, which is relatively intuitive, or you can take the approach that Josh put, which is to do this bit shift. And Josh wrote this, probably faster and arguably as clear. I have questions. I have doubts. So there's this wonderful book that was published in the 2000s, edited by Andy Oram and Greg Wilson, called Beautiful Code, and it included lots of different examples of people going into pieces of code that they loved or thought were great in some way and exploring those in detail. But one of the pieces actually looked at how to deal with testing this code and the bug that was in there. It was written by Alberto Savoia, a really good piece on testing and how to think in these terms. But Alberto points out, he says, probably faster, but may be obscure to most Java developers, including me. I'm going to tell you it is obscure to most Java developers. If you are thinking that you're going to keep right shifting instead of doing division, step away from the keyboard, okay? Go and talk to somebody who knows something about JVMs and compilers. One good piece of advice that we do find in the Bentley paper that is durable is keeping the code simple is usually the key to correctness. But ironically enough, there's a point here in More Programming Pearls, collected by John Bentley. He collects a number of observations from different developers and luminaries in the software world. And this is, the late 1980s or early 1990s. From Guy Steele Jr., if the programmer can simulate a construct faster than the compiler can implement the construct itself, then the compiler writer has blown it badly. In other words, if you're doing the job of the compiler writer, either you don't know what you're doing or the compiler writer doesn't know what they're doing. And he wrote this 30 years ago, before most of the wave of optimizing this stuff. As Josh says, the general lesson I take away from this bug is humility. Which is an important thing because we opened with that. April Wenzel's compassionate coding values. It is hard to write even the smallest piece of code correctly. And our whole world runs on big, complex pieces of code. And that's true. But actually, a lot of our world runs on surprisingly small pieces of code. Let me take you back to 2020. Yeah, I know, that was a year that sucked. But guidelines for human gene nomenclature. There was a issue. So in the space of genetics, genes are named, as in this is your genetic code. It gets named and classified. And the names are normally abbreviations. And they issued a new set of guidelines for how things should be named. And they renamed a bunch of genes that had already been named over the previous decades. Why would they do this? They would do this because of Excel, specifically bugs. I want you to look here and look at all these things. These all look like dates. They're not dates. They're gene names. And Excel is I think spreadsheets are a really cool idea, but Excel is a terrible, we've had this bug. It's not unique to Excel. Spreadsheets are a terrible, terrible development tool. They are a development tool. They are a programming system. But rather than value the things that developers value, which is to make things explicit, these things hide things away. The type system of Excel does all these conversions that make JavaScript look positively statically typed. Indeed, what led to this, a programmatic scan of leading genomics journals reveals that approximately 1/5 of papers with supplementary Excel gene lists contained erroneous gene name conversions as a result of this. We also see other consequences. In 2010, this paper was published, Growth in a Time of Debt, by Carl Reinhardt and Kenneth Rogoff. This paper reached the conclusion that under certain conditions of national debt and certain ratios related to that, the economy would contract. And this paper was used to support austerity economics, which intuitively is of an incredibly bad idea. But actually it turns out, and they were saying, actually, it's a good idea. It's a good thing. If you change these figures, then you get this. There's only one problem. There's bugs in this paper. There's a number of issues. This is a paper that takes it down. But one of the things is that they missed out 5 rows of data in their Excel. And it wasn't obvious because it's not a proper Excel is a programming system. It's just not very good at doing that from the point of view of what we know as developers and the tools that we use. And so they left out 5 rows of data. It turns out that when you include those 5 rows, the real GDP growth rate for countries carrying a public debt to GDP ratio over 90%, which is the critical factor quoted in the original paper, is actually 2.2%. In other words, there is growth rather than shrinkage, minus 0.1%. They got it wrong. It was a spreadsheet bug, a bug in their spreadsheet, and it supported a wave of austerity economics that has harmed people immensely over the last decade. So yeah, that's code. Now, some people say, oh, Excel, particularly developers say, oh, Excel, that's not programming. I have bad news for you. It very much is a programming system. It's a data flow system. Simon Peyton-Jones, known for his work in Haskell, often says Excel is the world's most popular functional language, which I'm sure upsets a number of programmers who, having spent years trying to get into functional programming, discover that everybody in the accounts department of their company actually has been doing functional programming for longer. But obviously with a far worse type system. It's not a Hindley-Milner type system. It's a kind of like convert everything maybe kind of system. But it actually got even deeper credentials. December 2020, okay? 2020, very bad year. Excel included lambdas. It now has lambdas, and indeed Google Spreadsheets also has lambdas. With Lambda, Excel has become not simply a programming system, it always was, it's become Turing complete, which is slightly frightening. So I can't imagine most Excel power users using lambdas, and I'm quite concerned if they do. But hey, it does make working with Excel even more fun. I put fun in quotes than it was before. So let's pick up on these things, because what is Excel? Excel is a big table-driven thing. And many developers say, oh, well, that's just data. That's not code. Oh, it's got a few formulas in it, but that's not code. It is code. It very much is code. So let's demonstrate this. Again, we have another way of thinking about this stuff. That's going to implement this Roman numeral conversion. To make sure that it works, I'm going to write some test code. Now, I'm not going to use a testing framework. What I've got here is I've written tests. I've written basically, I've written an array which contains data. I've then written another, or a list. I've now got another list. So this is, I've got names. Notice here, I'm not using comments, I'm actually using strings. If you can possibly put the knowledge into your test, then make it real. Use names that will mean something to people. And then I've got associations. There's association between 1 and I and 10 and X and so on. I've categorized these. And then I now go through this and I generate a new list, which is the list of failures where the conversions failed. And then I assert that there weren't any failures, and then I list out the failures. So this is a kind of like how to do testing without a testing framework in Python. But let's go through and classify the way that normally developers will classify this. The first thing, so hang on, I want to pick up on a comment from Alexander about what I said, Excel is the world's most popular functional language. He mentioned if VBA is not used. Yes, when we say Excel, we mean the Excel macro language. VBA is a separate language. Excel has 2 language systems. Okay, so I did not make that clear. So thank you very much for highlighting that. But yeah, unit testing the spreadsheets is actually a good idea from Christian. There are actually some good examples of doing that. You can do that in terms of conditional formatting and expectations. And actually, this is a really good example. Try doing Roman numerals kata in Excel. That's great fun. Anyway, back to this. The way that most developers would look at this, they go, oh, that's just data, Kevlin. That's not really code. And let's have a look here. What have we got? We've got, this is more data. So I've got 2 data constructs here, one depending on the other. One is derived from the other. So that's data. This is the bit we might recognize as code. And we might also recognize this as code. So the code is in the data is in the code, or is it all code, or is it all data? You see, we play with these words, and we do so with some ambiguity. And humans in our communication, we're normally comfortable with this kind of level of ambiguity, but we need to be aware that we are engaging in it. So one way to implement it would be to do this very procedural kind of thing, which leads to this kind of code, which I think is which is fine as a first draft. If you get your tests passing, that's great. But this is not the thing you want to check in. This is not the thing you want people to come back to. So I don't think this is a good example. I regard this as a failure mode implementation if this is what you're going to actually check in. Interestingly enough, this is one of this code. I was stumbling through an old Pascal book. I kind of like old books on computing. I was stumbling through an old Pascal book, and I found exactly this logic here. That logic that I've just told you, don't do this, this is not good programming, is what is used in the Pascal book. And Pascal used to be associated with good programming practice. I find Pascal one of the most annoying languages I've ever used. I don't think anybody actually likes Pascal. I think that's a myth. The only people who like Pascal, occasionally I get comments, somebody says, oh yeah, but I use Delphi and that's really good. That's not Pascal, that's extended. The language is not good enough on its own. The only versions of Pascal people ever liked were the ones that were not Pascal. In other words, they were always extended to make up for its deficiencies. And Pascal is very poor at expressing declarative data and being able to do data-driven programming. Data-driven programming is the way we want to think about this problem. And again, we might say, well, this is data and this is the code, but it's inside a function, so is it all code? Notice there's ambiguity here. But more importantly, this declarative approach, the use of tables and data to drive things, moving away from highly procedural code, which I see more and more of these days, especially when people say, oh, I'm using a functional style, typically in a hybrid language. What they're actually doing is they end up with code that is even more imperative than some of the code that people used to write in the 70s and 80s, partly because they're not aware of certain techniques and how to truly refactor things from a different point of view. Now, the late Fred Brooks, who died just a couple of weeks ago, last week, in fact, I think, the Mythical Man Month, he had this observation: representation is the essence of programming. Sometimes the strategic breakthrough will be a new algorithm. Much more often, strategic breakthrough will come from redoing the representation of the data or tables. This is where the heart of the program lies. And it's a really important point about how we think about these relationships: data structures, algorithms, the old school stuff of computer science. Data and code is the way many people think about it. So let's go back to that code. I'm going to do one thing here. I'm going to lift that numerals list out of the function. So the function is code, and this is data. I've made a data and code separation, where previously it was combined. I've made a data code separation. In fact, now I'm going to separate it even more. I'm going to put that list in a separate module. And in that module, I've got this. So I've got code in one place, data in another. Now I'm going to do something slightly weird. I'm going to turn that data into a string. Why would I do that? And then I'm going to evaluate it. Eval is an idea that goes all the way back to languages like Lisp, where you can actually take a string and then turn it into code. So the string, is this string a string, or is this string code, or is it both? That's the point. Again, we have this really interesting idea. But next, I'm going to do another thing. I'm going to get rid of all that other stuff. And I want you to look at the definition that we got up there. Is that code or is that not code? I've been cheating slightly. I've used a subset for the way that I've written the Python. This is valid Python. It's a valid Python expression. It's also valid JSON. And I can do an eval over here. Now, that's a little uncomfortable for some people to do it like that. So we'll actually use proper JSON conversion. But what you see here is that is effectively a configuration. I'm basically loading a configuration that I'm then running code across, which leads to the question, what then is configuration? Configuration is a formal structure for specifying how some aspect of software should run. In other words, it's code. And people have a blind spot to this. I've had people say, oh, no, Kevlin, configuration is not code. No, it really is. You're using a formal notation. Yeah, that's code. Yeah, but it's not code like my Java, like my C#. All right. Does it affect how your program runs? Oh, yeah, completely. Okay. So that's code. Hey, I'm using loads of dependency injection and I've got this XML. That's code. Oh, no, it isn't. Okay, does your system run without it? In fact, it actually defines the arrangements of your code. It is code. We just have a blind spot. We say, oh, this is code because it has if statements or whiles and things like that. And then everything else gets treated as a second-class citizen, including testing it. So 2017, there was a launch. Russian Space Agency failed to launch 19 satellites from Vostochny. Vostochny is in the far east of Russia. Normally, historically, they had launched either from Baikonur in Kazakhstan or Plesetsk, which are much further west. What happened? Well, all the hardware worked. The problem is, almost unbelievably, the flight control system on the frigate did not have the correct settings for the mission originating from the new launch site in Vostochny. They had moved where the launch was. The first two stages of the rocket were okay, but the last stage believed that it was being launched from somewhere much further west. So when the last stage orients itself, it's going like, oh man, I am so far off course. And it burns fuel to get back to where it thinks it should be. It runs out of fuel around Iceland and is observed re-entering entering the Earth's atmosphere by a British Airways flight. That's configuration. And we also have observations. Configuration errors are a huge, huge problem in code. And there's a lovely term, latent configuration errors, LCEs. Our study shows many of today's mature, widely used software systems are subject to latent configuration errors. People don't test their configurations. They find out the problems too late in runtime. And they also don't detect that in their code. They leave it until the point the configuration is used to test it, rather than the point the configuration is loaded into the code. Now, I'm going to go a couple of minutes over time. I hope that's okay with you. I want to talk about strings again. This is a string from the, this is a piece of code from the Mars Curiosity probe. It's the filler packet. It's 1095 bytes long. It's a string, and whenever Mars Curiosity doesn't have any data to send, it sends this as a filler packet. And you can see it's done in the Star Wars scroll style. And everything is relevant here. Lots of goody little Easter eggs and so on here. Now, this idea about strings being code is probably best illustrated by XKCD, Little Bobby Tables. Hi, this is your son's school. We're having some computer trouble. Oh dear. Did he break something? In a way. Did you really name your son Robert, drop table students? Oh yes, Little Bobby Tables, we call him. Well, we've just lost this year's student records. I hope you're happy. And I hope you've learned to sanitize your database inputs. Absolutely, absolutely classic stuff, this. Christian makes a point, opinion of configuration is code, then it often tends to be bad code. Yes, that's because we don't consider it to be code. In other words, because people don't consider it to be code, it drops down the kind of the hierarchy of our considerations. So we need to embrace it and go, why is it we don't tolerate this kind of code in our curly bracket stuff, but we do tolerate it in this? Well, we shouldn't do. It needs to be given some respect. Anyway, this Little Bobby Tables is kind of fun. Especially in the real world. So 2020 was clearly a fertile year for creativity. A company is forced to change the name that could be used to hack websites. A company in the UK registered its name as this. I mean, this is a great name. This is a great company name. However, a company's house in England said, you know, you've got to change your name. There's nothing wrong with their website, but if you use this name in other people's websites, it might be a problem. So they did rename the company name to that company whose name used to contain HTML script tags. Limited. So all we're seeing here is, as we write things, there's something about software. Software is made up. We make things up. We make things up and express ideas through them. The constructs are our choice. We have a lot of choices about how we literally encode things. This led me to say on a number of occasions that software is executable fiction. because it is fiction. It is made up. It doesn't have to be like this. We have a number of choices about how to choose this. We can choose our paradigms, our programming languages, and still end up with software that is functionally equivalent. We have a lot of choices. If you like, a paradigm is a kind of an archetype. It's a script structure. But a more famous author, Tom Clancy, made this observation: the difference between reality and fiction. What is it? Fiction has to make sense. And this brings us into the realm of life. A study was done in 2010. An analysis was done of the internal structure of the Linux kernel, and it shows you the call graph. And what is interesting here is that this clearly highlights an API layer and fan in and reuse. There's a lot of stuff going on here. This is a deliberate human-based design. And then they compared it to the regulator framework for the E. coli bacteria. Life looks completely different. This is all redundancy and duplication. It doesn't follow modularity. Everything has failover and redundant, but it's not, and things don't happen in one place. They are spread out. All of those ideas of cohesion and coupling that we value so much in our own software are not present in life. Life does not make sense. It doesn't have to. It's classic structure and interpretation of computer programs. They make the point. Programs must be written for people to read and only incidentally for machines to execute. We value legibility, comprehensibility. We talk about techniques and practices to make our thoughts known through code. We value structures that are distinct and clear and cohesive. We value knowing what we're doing so we can see what's going on. And this applies to algorithms and data structures, or does it? Well, people have been applying machine learning techniques to data structures. They ended up actually having adaptive data structures. So now you can have runtime improvements. Our initial results show by using neural nets, we are able to outperform cache-optimized B trees by up to 70% in speed, while saving an order of magnitude in memory. That's fantastic. How would you debug it? How would you repeat that? How would you teach it to somebody else? We have an interesting challenge ahead of us, because now we're writing code that is not incomprehensible. In fact, we're not writing it. We're writing code that generates stuff we don't understand. Whereas the whole history of software development has been valued things we understand. You can put a premium on it. Alan Perlis made this observation. If you have a procedure with 10 parameters, you probably miss some. Okay, he's saying, 10, you probably need 11, maybe 12. Because you'll always think of something else that you need. He made this observation in the early 80s. And if you've ever had to deal with a method that has many arguments, you know the complexity it presents to you. So where are we heading at the moment? Well, GPT-4 is going to come out at some point. GPT-3, 175 billion parameters. And we don't know what any of them do. So we're now creating code that is intentionally incomprehensible. We weren't responsible for it. So XKCD on the case again. It's your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. But what if the answers are wrong? Actually, that question itself is interesting, but we'll leave that for another day. Just stir the pile until they start looking right. Which leads me to a conclusion. And I will take questions. I will follow up on some of the things that people have been saying. There's some really good stuff in the Slack discussion. So, definitely, as I said, spend some time looking at that. I'm going to spend some time going through, making sure I haven't missed anything. I'm going to get another coffee, but I want to leave you with this thought: the newest computer can merely compound at speed the oldest problem in the relations between human beings. And in the end, the communicator will be confronted with the old problem of what to say and how to say it. That is our challenge with code. Thank you very much.